And today we'll be looking at the Boolean algebra. We'll be looking at the De Morgan theorem and circuit that uses logic gates. Okay. My name, you already know my name. And so let me quickly share my screen with you. I'm Professor Akinlola Yinka. You already know that. And let's just go on with module 2 very quickly so that we don't waste too much time. We have so much to cover today. I just sincerely hope that we'll be able to achieve as much as possible. Okay? Those who are just coming in now, they will be distracting me to be admitting them into this class. And I don't think I need that distraction. Okay. Now, these are learning outcomes for this class. Okay? The idea is for us to be able to define what the Boolean algebra is all about and what are its applications in digital logic design and then digital computer design. It's a very important aspect of our computing system, how basic mathematics are linked to how computer design is done, okay? Then we'll also be able to look at various Boolean laws and rules, as well as the De Morgan theorem. We'll be able to look at that also. Then we will also be able to construct and simplify Boolean expression using truth tables. And lastly, we'll be able to design and interpret basic logic circuits using AND gates, using OR gates, using NOT gates, exclusive OR, and exclusive NOT, as well as their various functions. So I want to crave your indulgence to pay close attention to what we'll be doing. And I believe that at the end of this class, you are bound to have a very pleasant experience. So welcome once again. Now, let's start with this. Now, please don't try to record. Is that okay? Whatever function you have on the Zoom link you are using, you are not meant to play with them, please. Okay? Focus on the lecture, listen attentively to every instruction I will be passing across. That's the only way by which you can actually benefit maximally in this class. Okay? So please don't play with any control. Okay? Now, let's go through some basic definitions. What is Boolean? When we say Boolean, what do we really mean? Or what does that, or what does it translate to? When we say Boolean, we're talking of binary value. This time around, your binary value could be true or false. It could be 0 or 1. It could be false or true. It could also be on or off, as the case may be. In the case of maybe you are designing an electric circuits. Okay, so when we talk about Boolean, we're talking of having a binary value. The word binary means binary by 2. Is that okay? 2 number system. Okay, so it could either be true or false. It could be 0 or 1. It could be on and off, and so on and so forth. So when we talk about Boolean, what should come to your mind is that we're talking about what? A binary value. Is that okay? And it's actually the foundation of digital logic design and computer science. If you recall in our introductory class, during the first class I had with you, I did mention to you that you should know that computer does not understand English language. Rather, it speaks based on the binary digits, okay? Binary digits, okay? And the binary digit that your computer works with is basically nothing but towards 0s and 1. When we talk about algebra, what is algebra? It's actually a branch of mathematics, and this one deals with symbols or basic rules by which those symbols can actually be manipulated. When we put the two together now, we're looking at Boolean algebra. It's actually a specific type of algebra. And what does it do? It actually deals with the Boolean value operations and then the various activity that can be carried out with them. Now, what about logic? Logic. When we talk about logic, because we are looking at the Boolean algebra and basic logic gates, that's what we're looking at. So when we talk about logic, what are we talking about? We're talking about the study of reasoning and arguments. the study of reasoning and argument. So if we bring that concept to computer science, we'll be looking at, oh, how best can I design an algorithm, or how best can I write a program to solve a particular problem, okay? So that reasoning, oh, if I want to do, maybe take for instance, I want to do a manipulation of 1 plus 1, okay? How do I go about it? Do I first of all create a variable for the first value before I will create the second one, or I will create the two and call them together? So the reasoning in a software engineering, it's actually called the business logic behind any operation you are doing. If you have complex operation, how do you how do you arrange them in sequence in such a way that as you take one, you take another one, or you want to take two functions together, how best can you actually optimize the system you are trying to build, or the program you are trying to write? Okay, it's possible you want to write a program to solve 1 plus 1, and one can take 2 minutes to run, while another one can take 10 seconds to run. What is different between the two programs? And maybe written in the same programming language. It could simply be as a result of what? As a result of the business logic that is behind whatever you're doing, okay? We also have another definition here. When we say Boolean logic, okay, we are talking about the specific type of logic this time around. This one deals basically with what? The Boolean values. You remember? We have already defined what Boolean is. We're talking about a binary value, zeros or one, okay? So when we talk about Boolean logic, we are looking at the specific type of logic by which we deal with Boolean value and the operations that we can carry out on them, okay? Then let's talk about gates. What are gates, okay? When I'm talking of gate, I'm not talking of the gate you have at the entrance of your school. No, I'm not talking about the gate that you have at the entrance of your house. No. When we talk about gate in the concept of this code, we're talking about the logic gates, okay? So when we talk about logic, what are we talking about? We're talking about electronic circuits. Electronic circuit, basically. Is that okay? But this electronic circuit, what do? They actually implement Boolean functions, okay? They implement Boolean functions, okay? So they have one or more inputs, or some of them can even have a single input, as we will see subsequently. And the output is determined by the kind of Boolean function that is implemented by the gates, okay? And we have common type of gates that you will come across in detail in the subsequent slide that I'll be showing you. We have the AND, OR, NOT, NAND, NOR. We have the exclusive OR, and we have the exclusive NOR. You will see them in detail shortly. Okay. Now, when we talk about Boolean algebra, I've said earlier, it's actually the word Boolean is named, or the algebra is actually named after the man by the name George Boole. Okay, what did he do? He's the one that actually introduced the concept around 18 something, around 19th century exactly. Okay, he was the one that introduced the concept, and this has become a part of the mathematical concept that is being taught day by day up to today. Okay, and it has various applications as far as computer design and then logic circuit design is very are concerned. Okay, now Boolean algebra, like we said earlier, two things have been established. We are dealing with what? The Boolean values, okay? We are dealing with Boolean values, which are basically what? Zeros and one. And it plays a basic role in the design of logic circuits, okay? Now, let's look at, for instance, if we have an AND operation, for instance, we have an AND operation, for instance. You will see the symbol, like I said, very shortly. An AND operation, for instance, okay? Let's assume you have a 2-input AND gate, for instance. When you have 2-input AND gates, only true. Is that okay? Only one true. It will only be true when you have all the inputs that are true. If you have AND operation, you will only have the output to be true when all inputs are what? Are true. If you have OR operation, it will only be true if at least one of the inputs is true. Please take note of this basic information there. It's different from just your normal mathematical operation of a multiplication and addition. No, okay? When we talk about the basic Boolean operation, and is key, or is key. Is that okay? Now, when we talk about and, I repeat, you will only have the output to be true only on one condition. The condition is that what? If all the inputs are true, okay? If it's an OR operation you are carrying out, it will only be true at the output if at least one of the outputs, one of the inputs, if it is true. And when we talk about NOT operation, what that one simply does is that it inverts whatever input is given to it. It inverts whatever input is given to it. It's just like an inverter. So what it simply does is that what? It inverts any operation it is given to. If you feed 0 into a NOT operator, it will give you 1. If you feed in 1, it will give you 0. That's basically how it works. Now, let's look at a truth table. What is truth table? Okay, I just brought up this for you to be able to see some of this. So when we talk about truth table, what's a truth table, or what role do they play? Now, truth table actually give you a clear visual representation, of the operation that is being carried out by your logic circuit or your logic gates. Okay, and on this table, I've just given you a very simple example of an AND gate, what it does, an OR gate, what it does, and a NOT gate, what it does. Now, let's look at it critically, and I want you to pay attention. I will quickly want to activate my pointer so that you'll be able to follow up what I'm trying to touch on the screen. Okay, now, let's take a look at this. I have an X and Y AND gate here, okay? An X and Y AND gate, meaning I have a 2-input AND gate, okay? I have a 2-input AND gate. You will see the formula that will determine the number of possible input that you can actually have in a particular gate, okay? You will see the formula very shortly. Now, but let's quickly work with this. Now, in this case, we look at the first condition. I can have 0, 0 for the 2 inputs, okay? I can then have 0 and 1. I can have 1 and 0, and I can have 1 and 1. So, meaning for a 2-input AND gate, okay? The number of combination I can have, it's actually what? 4, okay? I can have either 0, 0, 0, 1, 1, 0, 1, 1, okay? Now, remember what we said earlier when we are working with an AND gate. When we are working with an AND gate, what happened is that for an AND gate, for the output to be what? To be true, okay? It means all the input must be what? Must be true. If the output must be true, all the input must be true. And so if you look at the first one, 0 and 0, meaning it's not going to be true. 0 and 1, it's not going to be true. It will give us 0. 1 and 0, it will also give us 0. And here we have 1 and 1. That means we have an output of what? 1. Okay? If you come to an OR gate, we said whenever if just one of the input is true, then it means the output will be what? Will be true. Okay? Look at what we have now. We now have X, Y, meaning we are looking at X or Y. X or Y, X or Y. So we have 0 or 0, we give me 0. 1, 0 or 1. We have what? Because one of these input is already true, meaning I'm going to have what? True here. I have 1 or 0. One of my input is already true. Okay. Then I have 1. Then I have 1 or 1. It's going to also give me 1 because one of the input is already what? True. Now, let me quickly say this. Some people will try to use the concept of mathematics, teach this, and they will say, oh, 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, and 1 times 1 is what? 1. even though it holds in this place perfectly as an AND gate, taking AND gate as a multiplication, it may not always be valid. It is a way of just having it in mind that, yes, this can be as a guide for you. Okay, then let's look at this one as a function of 4. Looking at it as a plus. If you are looking at 4, it's a plus. Let's see the way it flows. We have 0 plus 0. This gives us 0, fine. We have 0 plus 1. This gives us what? 1. 1 plus 0 gives us what? 1. When you come here, 1 plus 1 will give you what? 2. That is where using the concept of mathematical notation we fail if you apply it hook, line, and sinker to the concept we're looking at. Okay? So please take note of that and pay close attention to the details thereof. Now, I haven't said that. Let's go ahead to go and look at a NOT gate. A NOT gate. Okay? Like I say, a NOT gate is just like an inverter. It takes 0 and gives you 1. It takes 1 and gives you what? 0. That's what it does, basically. Nothing more, nothing else. Okay? So in this case, we have an input of what? 0. And then we have 1 as the output. We have 1 as 0. Sorry, we have 1 as input. And here we have what? 0 as output. Now, let me quickly draw your attention to something very important and basic. Now, here, we call this one X complement. Is that okay? In some other places, you might see it as X bar. It's simply also telling you it's actually what? An inversion of X. So in some textbook, you may see it as X bar. You see it as S prime. Both of them represent the same thing. Okay. And what I've just explained is what you're seeing here at the lower part of this place. Okay. So now I've just listed some mathematical symbols that are very important for the next slide I'll be showing you. I'm particularly interested. When you see star here, it means what? A binary operation. Okay. So like I said earlier, it's a binary operator. Okay. Not necessarily a multiplication, and it could be an addition, multiplication, whatever in mathematical notation. I'm also interested in this symbol. We say it's an element of, okay, an element of, it belongs to a set, okay? And this one, not an element of, or it does not belong to that set, okay? So please take note of all this. We have an empty set, I think. Then here, you have other symbols that might be relevant. Now look at it. I'm looking at the most common axioms or basically the postulate of the algebraic structures, okay? And then we have about 6 of them that I've just listed here, 6 of them exactly, okay? And I'm going to just draw your attention to them and explain them as basic as I can in the next few minutes. Now we have the closure, okay? If you have a set, for instance, if you have a set, this time around, it's like you have a set of data, okay? Saying you have A, B, C, D, E, F. That is the set, okay? And then we have a binary operator. Remember, I've defined this earlier. We have a binary operator, okay? Now, the operation A and B, being a member of the set, it holds for all values of A and B being what? A member of that set that was earlier defined. Okay, so that is basically what the closure is talking about. We have the next one that is called the associativity, or what is simply called associative rule. Okay, what does it do? It says if you have a binary operation of A and B in bracket C, it can also hold that if you first of all operate B and C, and then you pull them together and then operate A on them, okay? It shows that this association holds for these two expressions. That is, you have a binary operation, you operate on A and B, and then before you go ahead to operate C on them, or you operate B on C first, and then you come around to come and operate A on them. That this association holds for set of A, B, and C being a member of a set, okay? The next one we are looking at is the identity element. The identity element. In this kind of a situation, if you have an element, say E, being a member of a set, such that A is operating on identity element E, okay? Then what is going to happen is that if you operate A on E or E on A, they will be equal and everything will still be equal to A. What is this one simply saying? E that you have here is just like saying having an identity element like 1, okay? If you have a binary operation you carry out on 1, for instance, you have 1 and A, okay? 1 and A, what will it give you? 1 and A, what will it give you? It will give you A, okay? If you also have 1 plus A, what will it give you? It will also give you what? A. Irrespective of binary operation you carry out on these identity elements to still return the value of A for you. Then the next one is the inverse element. The inverse element is simply referring to another element that simply inverts, like what we have earlier. When you feed in 0, then you come out with what? 1. It's just like an inversion. Next, number 5 is the commutative law. Okay. In this case, if you have A operated on B, that is, you have AB, then you have is equal to BA. Okay. If this equation holds for any of the binary operators or any of the Boolean expression you have for all values of A and B, then what we're saying is that such relationship holds for a commutative law. Okay. Then the last one is the distributive law. Okay. In this case, we're looking at if you have two operators, say you have and then you have an or. You combine them in this type of expression, you can as well break them down this way. Looks like a mathematics. If you have A and B plus A and into B plus C, okay, which is equal to, if you open this bracket, you say A, like multiply by B, you have A operating on B with this particular binary operator you have here. And then this plus coming and operator comes in here. You also have A with this binary operator operating on what? Operating on C. So if this relationship holds, and then you go to the other side of it, you also express it this way. If it holds, then we say such Boolean expression based the distributive law or distributive axioms of Boolean expression. Okay, I move on. Now, let's look at the basic operators that we have in Boolean expression. The first one is the binary operator that is defined as the addition. Okay, this addition, you know what it stands for? We are referring to or, as the case may be. Okay, then we have the additive identity, like I mentioned earlier. In this case, if I have the value of 0, A plus 0 will give me A. What if I have 1? A plus 1, what will it give me 2? It will still give me A. Okay, that is the identity we're talking about. What about the additive inverse? Okay, this one simply defines subtraction. That is, for every value of A, there exists minus A, such that if you say A plus minus A, only give you to give you 0. If you have an identity inverse that is added to the main value, you will come up with what? With a null identity. Then we have the binary operator that talks about multiplication. We have the multiplicative identity. The value is 1, such that if you have 1 dot 1, you also come up with what? It will come up with A. Okay. Then you have the multiplicative inverse. For a value of A not equal to 0, the multiplicative inverse will be what? 1 divided by A, where A dots into 1 over A, we also come up with what? 1. These are just basic postulate or a formula. And lastly, the distributive. I've explained this earlier. It's just like you want to open this bracket, and then you come up with what you have done there. Now, let's look at the practical implication of this distributive law for a typical 3-input logic gates. Okay, these are 3 inputs. We have X, Y, and Z. Now, for a 3-input logic gate, definitely we're going to have 8 combination. I will show you the formula, like I said, very shortly. Okay. Now, in this case, now, if you have this expression, if you open it up, let's verify if this distributive flow actually is correct the way we have opened it up this way. I don't know if you're following. I want to believe so you're following. Okay, now, if you have x multiplied by y plus z, and you open the bracket up, can we verify using truth table to see whether this is actually true? Yes, we can. Let's go step by step. The first thing we want to first of all establish is that let's first of all get our y plus z, that is y or z, y or z. Okay, if you go for y or z, now let's look at this is y column, this is z column. Attention at this junction, everybody. Now, if at this junction we're looking at this, now we have 0 or 0. That will give us what? 0. Okay. Then the next one we have 0 or 1 to give us 1. 1 or 0 we give us 1. 1 or 1 we give us 1. 0 or 0 we give us 0. 0 or 1 we give us 1. 1 or 0 we give us 1. 1 or 1 we give us what? 1. We are done with y plus z. Okay. What do we need again in this expression? We actually need to get what? The whole of this left side of this equation. Can we get it? So we now take x and this one we have gotten now. So these are column x. This column x. We are taking this column x. We are operating this column x with this y plus z we have just gotten now. So we proceed. So we come here and say 0 and 0. That will give us 0. Okay. This is the one we are operating now. We're operating this one now. We've gotten this. This is a column. We have gotten this, which is already given here. Okay, so I pick 0 and 0. We give me 0. 0 and 1, 0. 0 and 1, 0. 0 and 1, 0. 1 and 0, 0. 1 and 1, 1. 1 and 1, 1. 1 and 1, 1. So we have gotten this whole left side of this expression up to this point. And we verify what we have on the right side, right-hand side, whether this distributive flow is actually correct or not. We are proving it. Okay. Now, the first part we have here is what? X and y. So this is our x, this is our y. This is the column we are getting now. Okay, x and y. So x and y is 0 and 0. 0, 0 and 1, 0. 0 and 1, 0. 0 and 1, 0. 1 and 0, 0. 1 and 0, 0. 1 and 1, 1. 1 and 1, 1. So we're done with that. Okay. We do for x and z. This is x and z. Okay. So we go ahead to do that too. X and z. And we'll report the column here. X and z. So let's start. 0 and 0. It's giving us 0. 0 and 1. 0. 0 and 0. 0. 0 and 1. 0. 1 and 0. 0. 1 and 1. 1. 1 and 0. 0. 1 and 1. We have 1. So we are done with this. Okay. And then we go ahead to do the final operation here. So we have gotten this, which is this column. We have gotten this, which is this column. We go ahead and then do this operation on these two columns. These two columns now, we operate it with this 4. Okay. So we come up here, we have what? We have 0 or 0, 0, 0 or 0, 0, 0 or 0, 0 or 0, 0 or 0, 0 or 1, 1 or 0, 0 or 1, 1, 1 or 0, 1, 1 or 1, 1. So if we now compare what we have here, which is the right-hand side, to what we have here on the left-hand side, we will discover that we have exactly the same thing. Meaning what? This distributive law puts. Okay, based on this proof we have done using the what? The truth table. Maybe I should pause and take one or two response before I will continue. Do you have any comments, questions? You can unmute yourself before I will go to the next one. Hello, can you unmute yourself and speak if you have any question, comments? Let me be sure I'm speaking to you.
I don't understand.
Which part you don't understand? Be specific.
The part before this part.
Which part? Explain yourself, young lady. Hello, can you speak out?
That part that is like X, Y, Z, and all those three numbers on that.
Okay, I will take my time to explain this again. And let me warn those of you who are not cultured and you use all type of language in any forum where you find yourself. Let me quickly caution you very quickly. This meeting is being recorded. Are you getting me now? Those of you who are typing certain messages on the chat, you need to caution yourself, okay? You need to caution yourself. You are in an academic environment and there is a level of decorum that is expected of you. When you want to ask any question as regards anything, there must be certain level of decorum in asking your question. You understand it now? You cannot be insultive to any lecturer. You cannot even be insultive to your colleagues, okay? I saw some of you are asking, you want to take attendance and then they walk away. You could have swear, walk away from the class. Is that okay? You don't need to ask me when I want to take attendance or how I want to take my attendance. That should be at my own prerogative. And I will appreciate if each and every one of you can be responsible to how you act and conduct yourself. Is that okay? The degree you are earning at the end of your stay in the university is usually given both in academic and character. And your university is trying to build you in character. Part of it is that when you come to this kind of public forum, you should maintain highest level of responsibility. And I believe that is taken. That's all right. So I will go back to answer your question, young lady. Now, the distributive law, look at what the law says. If you have this type of expression, I believe you can see my cursor moving, right? Can you see my pointer? Hello? The lady that
yes, sir.
Yes. We need to respond if I'm actually attending to specific things. I'm not just here to teach. I want you to understand the basis of what we're doing. Even though we're a virtual environment, you can still gain the experience that you need to gain. Okay, now, so you can say this. We have X. This dot you are seeing here is an AND operator. Okay? Then you also have Y plus Z. Y plus Z, which is an operator. Okay? Now, maybe I should go back. Let me go to my previous slide. Take a look at what I have in this place. If you have 0 plus 0, we said is equal to 0. Okay? And that is what we're having here. Plus here. Talking about this OR gate. And I defined it earlier that an OR gate will return a positive true value whenever any of the inputs as positive. Okay? The A part is talking about this OR gate, and you have 0 plus 0 is giving you 0 here. Here you also have 0 plus 0. Or if you look at it from the English perspective, 0 or 1. 0 or 1, we give you what? 1, okay? So that's why you have this. Or if you have 1 or 0, 1 plus 0, we give you, and this one is even standing with normal mathematics. If you have 0 plus 1, it will give you 1. 1 plus 0 will give you 1. Okay? And I've explained that earlier by using normal mathematical notation. Also look at the hand. If you have 1 and 1, mathematically this one is also standing. 1 times 1 will give you 1. Then 1 times 0 will give you 0. 0 times 1 will give you 0. Okay? I talked about not. Not is that if you have 0 as input, then you get 1 at the output. If you have 1 at the input, you get 0 at the output. So please pay attention to the basics here. So the basic here is the one we are trying to apply to now prove that if this expression is true, if I give you this equation in mathematics, you can open this bracket now, right? If you open this bracket, x times y plus z, to give you x what? Times y, put it in bracket, plus x times z. If you open this bracket, that's simply what is being done. That is what the distributive law is talking about. I'm not saying by making use of truth table. You need to pay attention because I'm giving you assignment on this. Okay? So there is going to be a series of assignments I'm giving you in this lecture. And so you need the knowledge of this to be able to do it. Now, at this stage now, so we have this. We have this. And I'm saying let's try to prove it, whether this distributive law is true or not. And so we began. Because we have a three input logic gates, okay? Definitely we're going to have 8 different combinations. Like I said, you will see the formula for achieving that very shortly. So we have 8 combinations, okay? Now this 8 combination we have here, we want to start with this. We want to work on this left-hand side of this equation and get what it will be. Now we pick this one that is in the bracket. If you are solving mathematics, we first of all solve whatever is inside the bracket. And that is what we're trying to do here. So we have y plus z. Okay? So if I come with y plus z, I want to compute this column. This is my column y, and this is my what? Column z. Okay? So on my column y, I have 0 plus 0. That will give me 0. I have 0 plus 1. That will give me 1. I have 1 plus 0. That will give me 1. 1 plus 1 will give me 1. It will not give me 2. I've explained that earlier. Okay? I have 0 plus 0 will give me 0. 0 plus 1 will give me 1. 1 plus 0 will give me 1. And 1 plus 1 will give me 1. Okay? So we have computed this part of this expression. We're not done with the left-hand side. Okay? We haven't done this part. We need to now update it with this x. We have this column x here. Are we together? So what do? We pick this x one at a time and compare it with each of this one that we have also done. And then we come up with this. So what do? We have 0 here. And this is AND gate now, or multiply. So we won't use multiply because that might be confusing. Okay. So we have 0 and this. That will give me what? 0. I have 0 and 1 to give me 0. And you continue on and on and on, and you will come up with this column. Okay? So we are done with the left-hand side because we have gotten the whole of this expression in this table. Then the next one is you want to look at the right-hand side of the equation. And on the right-hand side, we have x and y. Okay? So which is this column? So we simply come here. This is our x and y. We pick them one after the other. We have 0 and 0. It will give me 0. 0 and 0 will give me 0. I continue on and on and on until I'm done with the last one. Okay? I haven't done this. I look at the equation again. I have x and z. I pick x and z to compute it here also. So this is my x, this is my z. I pick this and this. What will it give me? It will give me 0. This and 1. 0 and 1 will give me 0. 0 and 0. And I take it one after the other. I'm also done with this. Okay? And then I haven't done these two. I look at this formula again. What is combining these two parts is this OR gates. Okay? So this OR operator. What do? I pick this OR operator and then go ahead to operate it. So I have 0 or this. It gives me this, 0 or this, and I compute it, I got this. And so what do we want to check? We are comparing it. If you're saying this is equal to this, on the left-hand side, this is my left-hand side. On the right-hand side, this is my right-hand side. Are they equal? Yes, 0 is equal to 0, 0 is equal to 0, and on. 1 is equal to 1 until the last one. So that is the whole idea of this proof of this distributive law. I believe that is understood by everybody now. Can I get your response before I go ahead?
Yes, sir.
Okay, beautiful, beautiful, beautiful. So let's go to the next slide. Now, there are a number of postulation and theorem that were put together by Hunting. Now, in his postulation, he came up with what is called the duality principle. Please mute yourself. Hello. If you need to speak, please speak to me. Blossom, I'm distracting my class. Blossom, I'm distracting my class.
Present, sir.
Now, if you mute yourself again, Blossom, I'm going to remove you from the class and you disturb my class. Is that okay? So please, if you are not speaking, simply have to mute yourself, okay? Now, let's go ahead, please. Now, we have the duality principle. You have the A part of the postulate or the theorem. You have the B part, okay? So if you look at the postulate number 2, for instance, talking about if you have x plus 0, we have talked about this today, okay? It will give you x, okay? Because if x is 0, 0 plus 0 will give me 0. If x is 1, 1 plus 0 will give me 1. So x plus 0 will give me what? X. The same thing, if I have x and 1, will also give me x. Because if I have 1 and 1, it will give me 1. If I have x as 0, 0 and 1, will also give me what? 0. Okay? Those are some of the things that you need to just look at and how it works. Postulate number 5 by Hunting is x plus x prime. This one is the complement of x. Will give me 1. Because if x, for instance, 0, meaning its complement will be 1, meaning 0 plus 1 will give me 1. If x now become 1, its complement will be 0. 1 plus 0 will also give me what? 1. So this also puts irrespective of whatever you have for x. The same thing here, x and the complement of x will give me 0. All these things are things you can prove by simply putting 0 and 1, and then I try to see what it will turn out to be when you operate it. Then we have them on and on. And here we have our De Morgan's theorem that says that if you have x and y complement, it will give you what? S complement, y complement. And then you have the inverted expression of it, the duality of it, that says that what? X, y complement will also be what? S complement plus what? Y complement. Okay? All these can also be proven making use of what? Making use of truth table. And I think we'll have opportunity of seeing maybe one such very shortly. Now, let's take a look at one, for instance. Let's look at theorem 1, for instance. If you have this x plus x is equal to x, okay? We want to prove this. Now, you have x plus x here, and then you have your x plus x multiplied by 1, okay? Meaning, if we come up and say that what? X plus x bar, remember, we have defined this one to be equal to what? 1. And that's why we brought in this concept of 1, okay? Then, if you open up this bracket from here, we will come up with what? X plus x prime. Now, take a look at this. You can't have x squared. Remember, you are not doing basic mathematics. Rather, you are doing what? Boolean algebra, okay? So if you have x and x, what you are getting is what? X. Take note of that one. Okay, and then you go on. Okay, Shine, raising your hand. Can you unmute yourself and speak? Then let me hear you out. Or is it an unconscious thing? Shine,
No,
raising your hand.
sir.
You want to say something? Go ahead.
Why is x plus x prime 1?
What is what?
Why is x plus x prime 1?
Okay, let's go ahead to that one. Why is x plus x prime referring to this one, right? Okay, now let's try to prove it. If x is equal to 0, what will be x prime? Shine, you need to unmute yourself and respond to the question as we are discussing it. Okay? Shine, are you with me?
Okay, sir.
If x is 0, what will x prime be?
Yes.
What will x prime be?
X inverse.
No. If x is 1, what will x prime be? Remember, let me show you the table. Pay attention to this detail. Look at it. It's a NOT gate. So if you have 0 as x, what will x prime be? What will x prime be?
1.
And if x is 1, what will x prime be?
0.
I'm not hearing you. 0. So take note of that and pay attention
0.
to it. It's very crucial. Okay? So going back to what we're doing now. So
okay,
now take a look at it. So if we have 1 here, for instance, what will x prime be?
1.
If x is 1, what is x prime?
0.
You are not speaking out, a young lady. 0. Then meaning 1 plus 0. What will it give
0.
me? 1 plus 0. 1 or 0. What will it give me? It will give me 1. That is why we have 1 here. Okay. Now, what of if my x is now 1? What will my x prime be?
0.
If x is 0, then 1
0.
plus 0, what will it give me also? Yes, and then 1 plus 0 will give me what? 1. So either way, whichever way you do it, we always come up with what? 1 in this case. Okay? And if you come to this side also, if you have 0, for instance, this one is 1. 0 times 1 will give you what? 0. If you have 1,
0.
and this one is 0, so it will always give you 0. There are things that can be proven. Is that understood now?
Okay. Yes.
And so that is what is being proven here. And then if you have x and x prime, look at it. This s and s prime is what we have defined here. S times s prime is already 0. Okay? So that is what we bring here.
Yes.
And that is why x plus s will always give you what? X. Okay? That's a proof of that. And again, if you have x and x, we always give you what? X. Okay? So one can also be proven by following this simple step.
Yes.
Okay? Then let's quickly look at it's all right. So let's look at another one that can also be proven. If you have x plus xy is equal to x, x plus xy is equal to x. Okay, this one can also be proven. How can we go ahead? We've already gotten this. Then let's look at it. We are looking at the left-hand side. Okay, so if this is equal to not minus, please take note of this. S plus xy is equal to x. Okay, please take note of that. Now, I haven't gotten that. So we come up here. Instead of writing x, we change it to x dot 1. We have not changed anything because if you put x dot 1, we always give us what? X, like we have just proven now. Okay. Then if we now express it this way, by saying x into 1 plus y, okay, We also re-express this one. 1 plus y or y plus 1 is the same thing we're looking at, isn't it? Okay. And either way, 1 plus y or y plus 1 will always give us what? 1. Okay? Because we also saw it. It's just like saying x plus 1, like the question Shine was asking just now. So we have it as x dot what? 1. And by the time you say x and 1 again, you come up with what? X. Those are just the basic simple proof of all those things. And then let's quickly look at this also. We can also prove any of these things by actually using a truth table. Okay? This same one we have looked up here. Let's prove it using a truth table. We've gotten our x and y. Okay? Then we compute our x and y here. You already know how to do that one. 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0. 1 and 1 will give me 1. Okay? Then let's go ahead and do our what? X plus xy. We already have x, y here. Okay? This is x. Let's put them together. This or this will give me 0. 0 or 0 will give me 0. 1 or 0 will give me 1. 1 or 1 will give me 1. So if you look at this x plus xy, it's not the same thing as x. It is. Okay? So that's another way of proving that theorem, this theorem 6, A and B. Okay? Using a truth table, and then using the algebraic approach. Okay? So let's go on. The next one is the validity of De Morgan's theorem. See De Morgan's theorem given here. Okay? We're making use of a truth table to be able to also prove it. Yes. Dan, raising your hand, can you speak up? Dan, you raising your hand, can you speak up? Dan, you need to unmute yourself and speak if you are truly raising your hand and you're not just playing with the what you have before you. Okay, if it's not speaking, then I need to continue. Now, let's look at theorem number 5, which is De Morgan's theorem. Now, it's a 2 input we are dealing with, okay? So we can put our 2 input here is maximum of 4 we can have as input. So we have x, y, okay? So we have 0, 0. So what are we computing for? We first want to compute what? X plus y, okay? This is x plus y. So meaning 0 or 0 will give me 0, 0 or 1 will give me 1, 1 or 0 will give me 1, 1 or 1 will give me 1, okay? Perfect, we are done with this. Next one is I need a complement of this. When I'm saying of complement of this, I'm talking of an inversion of this. So where I have 0 becomes 1, where I have 1 will become 0. So the inversion here will give me what? 0 will become 1, 1 will become 0, 1 will become 0, 1 will become 0. And we are done with this s plus y prime. Okay? The next one, what do we need again? We need s prime and y prime. S prime is simply what? An inversion of x. So in place of 0, I have 1. In place of 0, I have 1. In place of 1, I have 0. In place of 1, I have 0. Okay, that's the inversion of x. The same thing we do for inversion of y. In place of 0, I have 1. In place of 1, I have 0. In place of 0, I have 1. In place of 1, I have 0. So I have the inversion of both x and y. Then I can then go ahead and do what? X and y. X and y, sorry, s prime and y prime. I can quickly go ahead and do that. So in doing that, I have 1 and 1 will give me 1. 1 and 0 will give me 0. 0 and 1 will give me 0. And 0 and 0 will give me 0. So I have this as my s prime, y prime. And we then compare it, s prime, y prime is the same thing as what? S plus y prime. So we've been able to prove this left-hand side of the what? Of the De Morgan's theorem. Okay? And then assignment number 1. Go and use truth table to prove this right-hand side of the Morgan theorem, this duality. I hope that is taken by everybody. Don't tell me you didn't get the question. I'm not going to repeat it. Okay? Do this. You will see some other assignment that I have in this work. Is that okay? This one is assignment number 1. Use truth table to validate this dual part of the De Morgan's theorem. I believe you know what to do. Put together, everyone? I believe so. Okay. Now, let's go to the next one.
Yes, sir.
Okay, good. Now, let's take a quick look at. Yes. Go ahead. If
Is
you have
this
any
the assignment?
The assignment, you understand the assignment? The assignment is what I've done for this A part of this De Morgan's theorem. Are we together? Do a truth table.
Yes, sir.
To also prove this right part of this equation. Okay?
I can't see it clearly. I can't see it clearly.
What is that you cannot see clearly?
The question.
You can zoom now. You can zoom. You can zoom on your phone, on your laptop. Yes.
I've seen it.
Good. Now, we have two Boolean expressions here, A and B. Okay? So we want to use the truth table to actually verify whether this is right or wrong. Okay? Shine, you can unmute yourself and speak.
I don't understand the question.
Okay, I will repeat the question. Hello? The question is simple. Are you listening, everyone?
Yes.
Now, what I've done in this truth table here is that I've verified this A part of De Morgan's theorem. Okay? That's x plus y prime, which is what I have here, is equal to what? S prime, y prime. That's what I've done. Okay? I'm now saying use truth table also to also verify this B part. I understood now. Use truth table, your own truth table now, verify this right parts. Okay? So with that now, you will now need to start. You already have x and y.
Okay.
Meaning you first of all do x and y. Meaning this column now will become s and y, x, y. And when you finish doing it, you will now take the s prime of it. And done. Then you also do the s prime, y prime. You already even have that one here. Instead of having s prime, y prime, you will now do s prime plus y prime. That's what we come here. You will now compare what you have to what you have here and what you have here. So that's what you're doing in that place. I believe that is taking by everybody now. Now the same concept is what you want to learn here. I won't spend so much time here. I said show that these Boolean expressions are true using algebra. Now, the first part is that we're using algebra. And the second part, which is an assignment for you, is to also use the truth table for these two expressions. Okay? So you have about 3 expressions you are working with now. The first one is the second part of the De Morgan's theorem, while the other 2 are these ones that you're seeing on the screen. So I will quickly show you how this is done using what? Using the Boolean expression to actually simplify it and prove it. That is what you have on the screen in this case now. So we want to come from this left-hand side to this right-hand side. How do we proceed? We have this left-hand side. So we open the brackets. Okay? We have x and x, x and z, y and x, then y and z. Just like opening the bracket the way you do the normal mathematical algebra. Okay? Haven't done that. We know that s dot x is x. I believe we all know that. So that's the first one we brought to bear here. That x dot x is equal to x. Okay? So we retain this in the place of x. Then we have every other expression. We retain them here. Okay? Now, having done that, we also go ahead and then look at if you have x into 1 plus z, like just bringing these two together. Okay? We have x, like you want to factorize. Okay? So we have x into 1 plus z. That's what we've got. Because if you open up this bracket, you will still get exactly what you have here, isn't it? So, having done that one, then we bring up the other expression the way they are. Then, looking at these two expressions, we said everything reduces to x. Why? Because if you have 1 plus z, is that okay? It will always come back to what? To 0. Are you getting me now? We are sorry, it will always come back to 1. Sorry. 1 plus Z. We always come back with what? 1. We have said that one earlier. You getting me now? And you can try it. If you put 0 here, 1 plus 0 will give you 1. If you put 1 here, 1 plus 1 will also give you what? 1. Okay? And so that settles that. So if 1 plus Z is equal to what? Is equal to 1, then meaning the whole of this one remain as what? X. Okay? We use the same approach here also. We have X, we factorize here again. X into 1 plus Y. We close the bracket and we bring up this one again. 1 plus Y will also be equal to what? 1. Okay? So, meaning the whole of this one will also be reduced to what? X. And then I will be left with what? X plus YZ, which is what we have here on the right-hand side. And we've been able to prove that. I take question or comments on this to be sure that you understand what I've just explained. Yes, question or comments?
I don't understand this part.
Which part you don't understand? Which part you don't understand? It's very important you go specific to the one you don't understand. Yes, I'm listening. Which parts? Pick out now. Which parts you don't understand?
I'm not so clear with the solution for the X plus Y into X plus Z equals to X plus Y Z.
I said which of them? Which of them? Which parts? Is it the first line or everything? Because, you know, I love students to ask specific questions, not generic questions. Is that okay? Are you still seeing my screen?
Yes, yes, I can.
Okay, let me try and go over again. Now, take a look at what we have. This is the left-hand side. We want to prove that it is actually equal to this right-hand side. Okay? Maybe you are also raising your hand. Do you have question?
Yes, sir. Good evening, sir.
Explanation. Yes.
And sir, please, can we like get this material you're using as an illustration for us to like go through later?
Young man, I've always given you guys lecture material. I don't expect that question to come from you, meaning you have not been following me. And probably
yes,
you have also joined the lab. You have not
yes,
joined. If you have joined,
yes,
you will know that I give materials. If you have joined, then don't ask me that question. Pay attention to what I'm explaining. Okay? Can I go ahead and explain now? Now, what we are having here is this. We have this left-hand side. We want to prove that it's actually equal to the right-hand side. Okay? And so how do we prove this? We started by applying the basic mathematics, okay? By opening the brackets. So we have x times x. We won't write it as x squared. Is that okay? Why do you think we cannot write it as x squared, if I may ask? We are not writing it as x squared because we are dealing with what? We are dealing with logic, okay? So we are not writing it as x squared because we are dealing with logic, okay? So we write it as what? X dot x. Then we have x multiplied by z. We have x dot z. Then we have y multiplied by x, y dot x, and then a plus y dot z. This is normal mathematics, so like opening the brackets. So I don't expect anybody to tell me you don't understand that. Okay? Now, we now began to apply some of the rules of the Boolean that we have established earlier and that we have proven using truth table. Okay? That if you have x dot x, it will give you x. Okay? That is, either way you put it, x dot x will give you x. And you can experiment it. If you have 0.0, are you getting me now? Sorry, 0.1. it will give you what? Sorry, 0.0 will give you 0, which is equal to x. If you have 1.1, it will give you 1, which is also equal to what? X. Are you getting me now? So irrespective of either you have 0 or 1, if you operate it on x.x, it will give you what? X. Is that understood by everybody, if I may ask?
Yes.
Is that understood by everybody?
Yes, sir.
Beautiful. Thank you. Now, so, and that is what made us to now reduce the whole of this to x here. And we brought about this. Instead of putting dots, we refuse to put dots, going further to simplify our expression. So we now have xz, we have yx, and the yz. Okay? Then, come in here. This is just like factorization now. If I have x plus xz, it means x is common to the two. I can factorize x, okay? So I then have x into x in x will give me 1. Plus x in xz, I'll be left with z, and I close the brackets. I don't think anybody should have an issue how we are able to come from here to here. Otherwise, we go and query your mathematics teacher that taught you in secondary school. Okay? So we came up with this. And when we look at 1 plus z, we already have an idea that if you have 1 plus z, it will always return 1, irrespective of how you do it. And you can actually try that and see how it actually works. By putting 0 here first and try it, what will you get? Then put 1 again and try it and see what do you get. We discover you always come up with 1. And so if this holds, then you have x.1 will give you what? X. So that is what made the whole of this one to also be reduced to what? Be reduced to x in this place. We brought in this one down. We brought this one down again. We can also factorize this the same way we did earlier. X is common. So we brought out x. And we have x in x. We have 1. X in y, x. We are left with y. And we close the bracket. We also brought this one down. We already know if we look at what is in the bracket here, we will always come up with 1. And so x.1 will give us x. Then we simply bring down this one. And if you look at what we now have as the last expression here, it's exactly equal to what we have here on the right-hand side, meaning we've been able to prove this by using algebra. Okay? Now the question is, can you also try to prove this using truth table? Go ahead and let that be your personal practice. It's not part of the assignment I'm giving. Okay, I think it's part of the assignment I'm giving you. So on your own, you need to practice and see how you can master some of these things. Then let's look at the second question. The same way we proceed also. We have this left-hand side, and that is what we have gotten here. Okay, how do we proceed? Here we have xy. Okay, we have xy into, because we have z and z prime common to this side. Follow me. So we have xy plus xy into z plus z prime plus xz, y plus y prime plus yz prime, x plus x. The reason why we introduce all that is because x plus x prime is equal to 1. Okay? So what we have simply done is to bring in this expression, wherever we can see x plus x prime, we are simply bringing 1 into the place. I don't know if you're getting it now. Look at this is xy you have here. We bring in the concept of z there. Okay? By simply saying the whole of this one is 1. So if you multiply it, it will just be equal to 1. Coming to this place too. Y is the one that is missing this middle one. So we bring in y. The whole of this one is equal to 1. Here, x is missing here. We brought in 1. But this time around, we are bringing in terms of what? In terms of x. Okay? And then we open all the brackets down. That's what we have done. We multiply them out. After multiplying them out, some of them we cancel out. Okay? Some of them we cancel out automatically. And so after canceling them out, let me even show you. Look at this. This plus this, xyz plus xyz. It will be equal to what? xyz. You getting me now? We have XYZ here. We have XYZ as the first one. Is that okay? So there's no need to repeat it. The same thing. We have Z prime somewhere. These two will also not be repeated. Okay? Because you know in logic, you don't have, if you have an OR operation, even if you have 1 plus 1 plus 1, it will be equal to what? 1. Okay? That is why the whole of this will be equal to just one of them. Okay? And then we have this one is unique. We don't have any other one. This one is unique. I think you are following me. Can you give me a thumb up if you are following me, please?
Yes, sir.
Thank you. Okay. Now, then we have gotten to this stage now. Then coming here, we are trying to rearrange, just simply rearranging, bringing them in a particular order so that it can give us where we are going. Okay. After rearranging, what is common here? We have factorized y and y prime in this place. Okay. So we have y plus y prime. Who is that person that is drawing up and down? Please don't do that. Okay. Then we have this xz, y plus y prime in these two. And we have yz prime. Then we have x and x. So the whole of this is 1, the whole of this is 1. And then coming here, we have exactly what we are trying to prove up here. Okay? So your next assignment is to go ahead and do what? And then show using the truth table that these Boolean expressions are true. So A, B, already have the first one for De Morgan. You are doing basically the same thing. Now, let me quickly introduce the concept of a Venn diagram. If you look at a Venn diagram, you are familiar with it in statistics. We also make use of it very well when it comes to a Boolean algebra. Okay, so I'm not going to dwell so much on it. It has its own functions and representation. Okay, now each of the cycle you have here represent different individual variables. Okay, and then you can have an intercept of variable at any point in time. You can as well also have different gates being brought out of this place in this Venn diagram. So I'm not going to dwell too much on it because of my time. Now, we've been talking about gate. So let's look at logic gate very quickly. And we have looked at the operations and how they work within the Boolean algebra. So, for instance, you have the AND gate, the OR gate, the NAND gate, and so on and so forth. Is that okay? Now, look at the way it is represented. I want to draw attention to this very quickly. This is not a NOT gate. This is an error here. Please don't pay attention to this. Now, here, you have your exclusive OR gates. Okay? This is the symbol for exclusive OR. And this is the exclusive NOR. That is not exclusive NOR. Exclusive NOR. Okay? So this bar is the NOR there, is the N there. Okay? So we understand how it works later. Now, these are the symbol for each of the gates. This is the AND gates. Okay? And this is the way it is expressed mathematically. We've been dealing with it since. This is OR gates. Now, this small dot at the end here is what differentiates AND and NAND. Okay? And when you are expressing it, you have bar top of the AND gate here. Okay? Then coming here again, you have the NOR, not OR gates. It's only this dot in front of the output that would tell you it is not OR gates, but rather it is a NOR gate. Okay? And you have this bar to represent it in the Boolean expression. Okay? Then you have the exclusive OR. This is the symbol that used to demarcate the exclusive OR. You have it here, exclusive OR. Okay? Now, in the case of exclusive OR, this is the way it is represented. Then you go ahead to have exclusive NOR. Exclusive NOR is only these dots. It's an inversion of the exclusive OR. Okay? And then you have, lastly, the NOT gate. You may also have another one that is called the buffer. Let me even show you. I think it's in the previous one. This is buffer. Is that okay? Whatever comes in here is what comes out. But in this case, the opposite of what comes in is what comes out. Okay? Why are some of you disconnecting and connecting again? Please stay connected and then stop distracting me to be admitting you all the time, please. Okay? Now, so here we have. Let me quickly talk about this not and. No, you know not and, that's easier. Let me talk about this exclusive OR. Now, the output is at logic 1 when one and only one of his inputs is at logic 1. It is exclusive OR, as the word is exclusive OR. Okay? Meaning, if you have 1 plus 1, it will not be positive, it will not be true. In the case of exclusive OR, you know, if it is OR, if you have 1 plus 1, it will give you what? It will give you 1. But in the case of exclusive OR, if you have 1 or 1, it will give you 0. Please take note of that. That's the basic difference you have in the exclusive OR. And then the exclusive NOR is just the inversion of that your exclusive OR, basically. Now, these are the truth table for various logic gates, okay? Talk about the buffer, whatever comes is what goes out. If you have 0 as the input, output is 0. If you have input as 1, is 1. In the case of NOT, whatever comes in, the opposite is what comes out. So if you have 0 coming in, 1 comes out. If you have 1 coming in, you have 0 coming out, okay? Then this is an AND gate. So for AND gate, 2 input AND gates, you have 4 combination, okay? I think we've been dealing with all of this, okay? Let me just go to exclusive OR. Look at it. This is exclusive OR. Unlike your OR, look at the difference between exclusive OR and OR. Everything is the same except this last one. Where in this case, you have 1 or 1. You have 1, okay? But here, 1 exclusive OR 1 will give you what? 0. Is that okay? So that's just the basic difference there. Please take note of it. And then the inversion of it is what gives you exclusive NOR. I believe this NAND is the opposite of AND, and then this OR is this NOR is the opposite of OR. Okay? Just to invert whatever you have as the output, that's what gives you NOR. Now, talking about the number of possible inputs if you have a logic gate, for instance. Now, the number of possible inputs will be given as 2 raised to power n. So if you have, for instance, 2 input logic gates, meaning 4 likely combination is what we have. Like we have been having here 0, 0, 0, 1, 1, 0, or 1, 1. Okay. If you have 2 raised to power 3, that gives you 8. And that's the highest we have dealt with so far. Okay. We have 8 different combinations that you can have. If you have, for instance, 4 input, 2 raised to power 4, you're going to get 16, I guess. Okay. So it continues on and on and on like that. Now, this is also another assignment you're going to do. I will just explain one to you very briefly. Okay. Now, let me mention the textbook I gave you. The textbook I gave you, we find some of this information there. For this particular circuit, I pick it from that textbook. Okay. What I'm expecting for you as solution is different from what you have in the textbook. Hence, you need to pay attention to what I want. Okay? So I'm going to be making use of this one, this A part, as my example to illustrate what you need to do. So pay attention to what I'll be doing as far as this is concerned. Now, remember, we have 3 inputs, X, Y, Z. Okay? So I'm not just interested in the final output. Are you listening to me, everybody? I'm interested in every output you get at every stage of this circuit. So in this case now, you already have X and Y and Z. I want to see a truth table column for Z prime that will come out here. If you want to do this for me, okay? I want to see the truth table column for this Z prime. If you are picking this, for instance, Y, I want to see the column for this Y prime in your own solution. And here now, you have Z and the what? Y prime coming in. You can choose any variable to represent this and draw it and put it in the diagram you will draw for me in your solution. For instance, you can call this one you have used Z and you can say this one is your Q. Is that okay? I want to see Q that is coming out of this AND gate. Okay? Your truth table. Before you will now combine your Q and X and tell me that is what give you F2. Okay? If you come to this one too, this one we have several columns. Okay? For instance, here you have what? you have your X prime. I want to see X prime in your column. Here you have your what? You have your Y prime here. Okay. Here, okay, you don't have, so you are, I want to see S prime and Y prime. Okay. I haven't seen that. Coming to this output now, I would like to see A. Okay. And A will be what? A will be your S prime and what? Y prime and what? Z. I want to see the output A as you progress in that place. Okay. I would also like to see the same thing for this. Here, I have X prime here. I have Y coming in here. I have Z coming in here. I want to see how you operate them and then to get your B and C and so on and so forth. And then I would like to see finally how you use this NOR gates to be able to give me exclusive OR gates rather. No, this is just OR gates. How you use this OR gates to be able to give me 3. I would like to see it. The same thing here. I have Y prime here. I have X prime here. I want to see the output here. Maybe you call it your JQ or whatever name you want to call it. I don't care. But I want to see it in your truth table as well as the diagram you will draw for me in solving this. Okay. So I said prepare detailed truth table for figure 1 to 4. But I'm going to show you what I've done for figure 1 very shortly. So this is my own figure 1. So here I have my X prime. Okay, I have my X prime here. That's what, sorry, Z prime. And that's what I've computed in this place. Okay, look at it. Z is here. Z prime is 1. 0 will become 1. 1 becomes 0. 0 becomes 1. 1 becomes 0. 0 becomes 1, and so on and so forth. I have my Z prime. The next thing is that I will now pick X, Y, and Z prime. Okay, meaning I'm applying AND them. So meaning I have X, Y, Z prime. So this and this and this will give me 0. This and this and this will give me 0. And I go on and on. This is the only place where I have 1, 1, and 1. It will give me 1. This one is 1, 1, and 0. It will give me 0. So that's how I've been able to get my F1. You will have several columns in the B, C, and D that you're going to do based on the explanation I have given. Time is fast going, so I need to actually conclude what I have for today. I will take questions generally thereafter. Now, practical examples of gates. We have practical AND gate, we have practical OR gates. And the example of IC for such is the 4000 IC series and 7400 IC series. Okay. For instance, this 4081, you have 4 pieces of 2 input AND gates inside, representing different pin of the IC. Okay. And then if you have an IC where you have this cut, that is where your pin 1 starts from. For every IC that you have on the computer, there's always this cut and this mark. Okay, they indicate, this cut indicates the top of the IC, and this dot represents where the number 1 should start counting from. Okay, so you have 1, 2, and on, and you count back upward there, the last pin. Okay, so here, if you need the input of the first AND gate inside, you have 1 and 2 to give you that. Okay, and it's giving us A1, B1. So meaning if you feed in 0 and you feed in 1 here, at display, what will you measure? 1 and 0 will give me what? 0. So that is what you have in that place, and that continue on and on. The same thing we have for that type of different type of ICs in that category. Okay, now let's look at a sample practical circuit where we can apply all this we've been talking about: logic gate, logic gate, logic gate. What are their practical applications or implications? Take a look quickly at this. The circuit you have here is just like you just want to power a simple LED bulb using a simple voltage source. And so I have the positive side of my voltage here, and I have the negative side, which is the ground here. Okay, and the VCC is connected through a switch here, can be switched on or off. And the negative side, which is the ground, is also connected to what? Connected to another switch. Okay, so if I have 0, 0 here going to display, definitely in the AND gate, I'm going to have 0, and then this light will not be on because the input is 0, 0. Okay, and if I go ahead and look at it, if I on this switch, meaning I connect it to VCC, and then this one is still left open, I will still not get any light in the output here. Okay, because 1 and 0 in the AND gate will also give me what? 0. And go ahead again, look at the next one. We come here, we also have 0 and 1. I'm still not going to get any light at the output. And if I have on and on, 1 and 1 in this place, meaning I'm going to have 1 at the output and this light will come up. That's a typical example of a practical application of the circuit, the logic circuit gates. Okay, and so in conclusion, we have looked at the Boolean algebra and then digital logic design, and I believe we've been able to look at what the Boolean laws are, the Morgan's theorem, and the rest of them. I also believe we've looked at the digital circuit, the basic application of some of these concepts of the Boolean operations. And on that note, I want to say a very good evening to you. And if you have questions this time around, you can then ask me. Yes, questions from anybody?
Sir, the total number of assignments you've given us is how many?
Yes. Time of assignments. You should count it by yourself now. Anyone that's supposed to count it for you. Count it by yourself. Count it by yourself. So
what are you talking about?
Which what?
Textbook.
I shared a textbook with you on the WhatsApp group. So if you have not been opening the textbook, go and be opening it, and then I'll be reading it. Okay?
Oh, yes, sir.
Yeah.
Hello, good evening, sir.
Question or comments? I have just 33 of you online.
Hello, good evening, sir.
Yes, hello, good evening.
Sir, please, I want to plead for the fact that I was in this class, I was going off and on due to network, and I don't actually know if we can get, you said something earlier that you gave us a textbook, which some of us have checked, and you also have what you want us to give to you due to your class work. So I don't know if you can help us with today's lesson as a PDF, sir.
You asked for too much. I've always given my lecture material out. Once I'm done with today's class, by tomorrow, you will have it. You'll be able to access it on the lab exchange.
Thank you very much, sir.
This were not listening.
Thank you, sir. Like I said, thank you, sir.
Your network was giving you issue. That's okay. Yes. Any other question or comment again?
Good evening, sir.
Good evening.
Sir, the assignment you gave us, when are we to submit it?
You can submit it tonight. But do the assignments. I can ask you to submit it anytime. So don't wait till next week. Okay.
Okay, sir.
The assignment should be done immediately. Do it. You understand it now? I may not ask for it in the next 2 weeks. I may not ask for it in the next 1 month. But when I will ask for the assignment, that's not when you will start to do it. It will not work for you that time. So in your own best interest, do it, and then just do it and keep it somewhere that if I ask for it, you'll just be able to submit it. So that's it. That's my advice. So, but you know, you can, a student can always say, we always want to have their way. But my advice is do it tonight and get it ready and keep it somewhere. I've done these assignments. Yeah. Any other question?
Yes. Sir, how often are we going to be having this virtual learning class?
As soon as I choose to have it. Why are you asking that question?
Sir, because a lot of students are having challenges entering the class.
Students will always have challenge. Are you getting me now? That's one thing I know about students. They will always have challenge doing what is right. So it's not new to me. Speak for them. If you are able to enter the class, nothing stops any other person from entry. The Zoom I'm using is a Zoom that is very sophisticated. So nobody has any excuse not to be able to enter. Are you getting me now?
Yes, sir.
So, and I've tried to be as flexible as possible to ensure I accommodate everybody. But you know, over the years, I've discovered you cannot always have every student on your side. But the only thing that will drag them closer to you is when you give them test. When you give them test, exam is around. So, but for me, like I've always advised, I advise everybody. I've been in the university system for almost 20 years. So I've related with different kind of students. You understand that? So in your own best interest, just follow my simple instruction and advice as far as this course is concerned. You have any issue. But if you try to be a smart one, the end result might not just be the best. That's my own simple advice I will give all of you. Any other one again?
Sir, is the
Yes, sir.
assignment going to be submitted online?
Do the assignment with your handwriting, draw the circuit, and do it on a piece of paper.
Hello,
Take a
sir.
photocopy for
I
yourself
have a
and keep
question.
it.
Okay, sir.
Yeah.
So still on the
Question.
assignment, for those people that were not around when you started.
How does that become my own business? So I'm hearing you, my dear young man. No.
Okay, sir. So good evening, sir.
Alpha, confirm TVK for that side of it.
Young man, please don't ask on behalf of anybody.
Play it for us.
Is that okay?
Sir?
Don't ask a question on behalf of anybody. Do you hear me?
No,
Okay, sir.
So those that
let
are
me
not
redirect
around,
my
not
question.
to be around.
Okay. I was not around when the meeting started.
So that you are not around, how does that become my business now? We're not told.
Play the assignment again.
Yes, sir. That was not.
I'm sorry, I'm not ready to repeat it again. Any other question again?
Let's move on. Previous question.
Now, listen to me and listen carefully. Listen to me and do what? Listen carefully. Some of you are asking questions. My internet, my network jumping up and down. When I was hearing some of you speaking at the background, there won't be another excuse this time around. So listen and listen carefully. Okay? I have 35 of you online now, 34 of you online now. Some are connecting and disconnecting. I don't care. So now, or let me say, I care less about what the challenges are because I know students will always play funny. That doesn't mean I don't care about your well-being. I care so much about your well-being. So let me reframe my words. Is that okay? But I know students can be very funny. That I've established over the years. Okay? So for the funny ones, the choice is purely yours. Okay? But I care about things that affect your well-being and your academic well-being. I haven't said that. Now, what is on ground now is that I'm going to give you a test. And listen carefully. Listen carefully. The question is very simple. Simple question. Listen. Don't try to go and call your friend to come and join. You know why? They cannot join now because I won't admit them. Okay? So listen for your own good. Leave your friend out for now. Struggle for yourself. Now, the instruction is this. I gave just two simple objective questions, which I will display now. Some of you are still talking at the background. No problem. I won't repeat myself. Two simple objective questions. Are you getting me now? Now, you will simply type your name, your math number in the chat menu. It's chat you will use to answer the question. And you have just 2 minutes to do it. Just 2 minutes. I won't listen to any excuse. So you are using chat. Nobody should type anything in the chat again now. The chat is going to take the test now. And in answering the question, what are you to do? Type your name in the chat. Type your math number in the chat. And I want to see A for question 1. Answer is A or B. Number 1, you put A. Then go to number 2. Is it B? You have just how many minutes to answer it? Just 2 minutes. And the time starts now. Do you understand how to answer the question? Or I should repeat myself?
Sir, repeat yourself, please.
Repeat yourself.
In answering the question, just 2 objective questions. That's what will come up in the next screen now. Just 2 objective questions. And you are to type your name, your math number in the chat menu of this Zoom meeting. And after typing your name and your math number, then put number 1, A or B or C or D. Then number 2, put A, B or C or D and submit the chat. And that will be all. In 2 minutes time, I'm going to stop this meeting, and that will be all. So I wish you success as you take this tea. Answer the two questions together. It's just one single chat I'm expecting from each of you. Seconds to go. Type whatever you want to type and submit. Okay, so I want to say very good evening to every one of you one more time. And that will be all for tonight. So do enjoy your evening. Yes. God bless you. Have a sweet, beautiful, and a lovely night rest.
Hallelujah.